inconveniences here. We want to show something interesting, and I just couldn't connect my laptop, so we will have to improvise a little. My name is Alex. I'm CEO and co-founder of Meta Labs. Wait. And then start again. Yeah. Okay.
Because they are live streaming.
I see. So he will give me a sign. He will give me a sign. Cool. Hi, everyone. Welcome to the talk about zkSync, the first EVM-compatible zkRollup. My name is Alex. I'm CEO and co-founder of Meta Labs. We are creators of zkSync. And I am just going to give you a few highlights, like what the system is able to provide. First of all, zkRollup is something that can combine the benefits of the rollup and sidechain worlds. So it's possible to extend it. You can not only have a zkRollup functionality, but you can have something we call zkPorter that gives you very cheap accounts. So we have two account types in zk system. One is zkRollup, which is ultra secure, it inherits the security properties of Ethereum, and one is zkPorter, which is ultra cheap, and they can seamlessly interoperate. Now, second thing, since it's a EVM-compatible zkRollup, you can deploy any existing Solidity contracts without modifications. So you don't have to change them, you don't have to re-audit them, you just deploy them and they work. And we preserve the full mainnet-like composability. So you can, one contract can call another, you can have atomic transactions spanning across multiple contracts. They can fail, they succeed, just the same way they work in Ethereum. In zkSync, we used to have a different language for programming contracts called Zinc. So we preserved it as well, and you can program Zinc and interoperate between Zinc and Solidity also seamlessly. And you can reuse the existing tooling. You can take the existing Ethereum wallets, which natively support a CDSA signature in zkRollup, and it works with existing tools because Web3 API is fully compatible on read-only level. For sending transactions, you need to slightly change the SDK, but your code will remain the same. You only need to make a few imports and use different properties there. And we actually wanted to show you a live demo, and this is why it took a bit longer to set up these things, because I cannot use my laptop. We connect someone from our team. Hi, Vlad. You should. So how do I do this? Wait. So I need to go here, over here. I'll put you on the sound. Say something?
No, you haven't put the sound
No,
on.
wait. Now.
Can you hear me now?
Yes, we can.
Yes, we can.
So we have a couple of contracts here. One is, Vlad, I'm going to put you on mute because otherwise it's echoing. Sorry. I'm just going to say. So we have a couple of contracts. One is written in Zinc, one is written in Solidity. We start with the Solidity one. It's a very simple one. We're still working on the compiler. Compiler does not support 100% of cases yet, so that's why the testnet is not public. But we are very close. Like we fixed the things in the LLVM backend, so the compiler is based on LLVM. We reuse all the tooling from there. And now we're fixing the final things for Solidity, but Zinc works very well. So this is, as you can see, it's a very simple contract. It has some storage value. It has some public methods, like a public method that can write this value, and an immutable public method that can get the value. So now we're going to compile it using Sol-C, which is a standard Solidity compiler, which produces the YUL output, and we pass it to the so YUL-C compiler gets us the EVM bytecode for, sorry, zk EVM bytecode, the bytecode which we use for our virtual machine, which is used in zkSync. So now we can deploy it. We have a simple tool to do operations on with contracts. It's called zcli, and we just take the bytecode which just been compiled, and we deploy it. Let me see if I can improve this. And by the way, I forgot to mention that this is a very spontaneous demo and expect it not to work. Something will probably go wrong now. Because we were not going to present it, but then last minute, like I asked the status and the guy said like it's actually almost ready, so like yeah, should work. So yeah, now we see the execution result. The execution executed was true. No error. Here is the actual bytecode for Zinc VM. You have the contract headers here and some other metadata, so it's now deployed. Now let's go over to the Zinc code, which is a bit more expanded. So we have two contracts here. One is just the interface, because Zinc is a subset of Rust. So we use like same approaches in Rust. We had to define, we have to adhere to strict typing, and we have like essentially an interface for a trait for what we're going to call in the other contract. So we just define the public methods here. And in the actual main ZN, we have the code of the contract itself. So it's essentially a proxy contract which just takes some target, and we can call methods on that target. The same way you would do it in Solidity. So we just like want to show you the interaction between Zinc and Solidity. So you have some public method to get. Get the count. So the counter is our target. It's the contract called target. So we just called it this way. And U160 is the type of for address. So yeah, this is the code. We can compile it with the Zinc compiler. It's going to be optimized. So we use all the optimization primitives we have from LLVM. I'm going to produce the binary code. It worked well. You can see it under debug, and we're going to deploy it with the same utility we use for deploying Solidity contracts. I think you need target with T.
So this is the exact same as writing the Solidity contract. You're just showing a different way to do the same thing, right?
Yeah, so we just support two languages now. We have front ends for these two languages to LLVM. They compile to LLVM intermediate representation, and then from there we have a single backend which compiles into the Zinc VM bytecode. So we have the bytecode, we have the exact same result, we deploy the contract at some address, and now we can go and try to interact with it. So maybe, Vlad, can you show us the Zinc Block Explorer first? So it's our public testnet. You can all go to the zkSync 2 alpha, zkScan.io, and you will see it. And yeah, can you show us some last transactions? We have a deploy contract transaction here. So it's permissionless to deploy. You just send the bytecode. The bytecode is public. Since it's a zkRollup, all contracts that are deployed will have the bytecode published through Ethereum. And now we can go and open. We built a very simple demo app yesterday, so please apologize the design. It's actually a beautiful design, I think. So we have two contracts here, and we have methods to interact with them. We support Web3. This version is done like we're calling native API, but the Web3 will be ready in like a few weeks to full use. So you can get the value from which is calling the function getValue and returns the value from the storage. This is our target contract written in Solidity. You can click increment value, and it will throw a MetaMask, or like you can connect any wallet. It can be like mobile wallet, anything that supports Web3. You sign the message. We use EAP 712 for signatures, and it's signed and submitted to the contract. It's actually executed. It's already updated the state of the rollup. And then we can go on the proxy contract and get the target value, which will invoke the other contract and and get the value there. So it's like they're already interoperable seamlessly in like mainnet style composability. Yeah, so that's the demo we wanted to show. So thank you, Vlad. We'll move now to the presentation and leave. Okay, so this is what's working now. We're waiting for the compiler to be fully ready and for the API to be fully tested before we can publish and open the testnet to everyone. We're not going to do like white lists, we're just going to open it public. So the question is, what are the limitations of this first version? So we call it zkSync version 2, but the release is going to be 0.1 or like whatever alpha. So first of all, in the contracts, we don't support precompiles yet. We don't support the cryptographic precompiles, such as EAP 1962 or like the pairing computation. If you want to do cryptography, that's not ready yet. But if you want to do cryptography, actually in the future it will be a lot easier because we will support recursive snarks natively, and they're going to be super cheap because you don't have to publish the actual proofs in a zkRollup or in zkPorter anyway. So no precompiles for now, although we support like all the hashes. We support Keccak hash, we support SHA-256, and we support algebraic hashes, which are much cheaper in snarks. So all your normal hashes will be replaced with algebraic hashes automatically, but you can fine-tune. You will be able to choose which one you actually need. I can explain later. We don't support cryptographic modular arithmetic. So there are a few opcodes in EVM called add mode, sub mode, mul mode, and I don't remember what else, X mode, I think. We will support them through the compiler. The compiler will produce the codes. We'll expand them into different codes. We don't have these opcodes natively in Zync VM, but you only need them again if you want to do cryptographic operations. If you're just writing normal DeFi contracts, NFTs, whatever, no one uses them. So like most people are fine. What we don't support, what is like a bit annoying, is we don't have EC recover for now, because we need a mechanism for our internal precompiles to add that, and it will take a bit longer. And we don't support creating other contracts yet, but it will be natively supported. So create two opcodes will for now fail, like we just won't compile. But they will be supported in the first version, so we have all the mechanisms for that as well. Okay. And so as I said, the read-only Web3 API is all these tools which I mentioned, like Etherscan, the graph, etc., etc. They can all work. They can just like go and subscribe for events, grab the data feed from our APIs, read, like execute the invoke methods on smart contracts. But if you need, like, it all works like just with existing APIs. If you want to send transactions, you can use the same signing mechanisms you already have in your apps or in your wallets, but you need to format the message slightly differently. Like we don't support the same format as Ethereum, although the API encoding of the transaction is actually the same. But unfortunately, we need to like make a hash of it before we submit it to the message. And we need to add a few other metadata parameters which Ethereum doesn't have, because like we support native metadata, we support natively timestamps, like validity timestamps. You can say this transaction is only valid for this many blocks. So this is all additional information which we need to pass somehow. So you need this intermediate step, but it's actually very easy to implement in your SDK. So we will support like all the usual SDKs. You can import like Ethers.js, for example, and just like add a wrapper that will do a different way of signing. Otherwise, you will not need to change your dApp in any way. Okay. So this is the overview. We can go into different topics in depth. I have a lot of slides here, but I want to make it a bit more interactive. So how much time we have? It's 20 minutes more. We can talk about the design of zkEVM in depth. We can talk about the hybrid zkRollup, zkPorter model of data availability and what impact it has on the applications, on the price, on the security of your accounts and how they interact. Or we can go into other questions from you guys if you're interested in something else. So like who want to talk about the zkPorter and zkRollup? Okay, who wants to talk about the zk EVM design? Okay, so we have more people who want zk EVM, so let's start with this. It's actually the next slide. Okay, how it works. Let's recap how rollups work in general. So you have some off-chain state, which is represented by your root hash, which is submitted to the smart contract on Ethereum, and it holds the state. And whenever you have an update of the state, we can define a state transition function that takes the previous root hash and produces the new root hash based on the input of like some array of transactions. And what we need to do with zkRollup specifically, we need to arithmetize this function to be able to produce proof of it. So to take the function and to produce a succinct proof that we actually computed it, and here is the result, and the result is valid, and we didn't skip any step. And this arithmetization process is what made it very difficult for us to implement Turing-complete Turing-complete zero-knowledge proof systems in the past. Because arithmetization means you take your function and you have to decompose it into a cyclic graph of operations where you have all the inputs of the function as like on the left side here, and then you have gates which represent arithmetic operations, and we only support two: modular addition and modular multiplication, and you get the result at the end. And this has to be a fixed, rigid circuit. So we call it arithmetic circuit, which is very similar to hardware circuits, how you like just put gadgets on a physical hardware board and connect them with wires. And you don't have back loops. That's why it's linear. It only flows in one direction. So the question is, how do you represent Turing-complete programs, which can have loops, can have conditionals, can have like different things depending on the data which you input, which you can't do it here, right? So you can have something only rigid, and the problem is some of the operations are going to be very expensive. So like if we need to implement like simple addition multiplication, it will take us just one gate because it's a native operation in this circuit. But if we need something like a SHA-256 hash or Kajak hash, God forbid, it's going to be like thousands and tens of thousands of those gates here with those operations. So it's like if you want to combine them and do something flexible, like it's gonna just get out of control in terms of costs. So how do we arithmetize generic computation? So I'm gonna like rush through the presentation because we don't have much time, but the general idea is we used an approach called TinyRAM. It's actually pretty old. It's 10 years or more, 14 years old, where we construct a circuit. It's like a single circuit which has, which can prove not just a fixed program, but it can prove the execution of arbitrary program, because at each step we prove the execution of all the possible opcodes which could have been used at this step, and then we only select the result of the opcode which actually corresponds to the input of this operation. Does this make sense? So like maybe. So this spreadsheet, I can't open it because it's it's a different laptop. But imagine a spreadsheet which has this formula on the right. Like if column D has this formula, like if the operation of the at this step is addition, then add the operands, or like add the operand to the previous value, to your accumulator, and take this value. If it's multiplication, then multiply it and take this value, and so on. So you can, if you read this formula and if you're proficient with Excel, you will immediately see what I mean. Like the formula at each step is the same, but depending on the operand in the column B, we will take different values. Like we will take different formulas. So like if the B10 is add, we will multiply it by 1, otherwise by 0. Plus, if it's sub, then we multiply 1 with the subtraction, and take this value instead, and we sum all of them, so we will only take one of the results.
Do you still compute each of the operation, even if you only...
Exactly, you still compute all of the operations, but you just like, then you computed all of them, and then you say, okay, this was addition, so let's take the additional, the result of the addition. If it was multiplication, let's take the result of multiplication. So as you can see, we need to produce like a quadratic complexity. So like we have the number of steps in our execution trace, and we have the number of operations in our virtual machine, and this is going to be your like the metrics which you need to build the circuit for. So it's pretty expensive, but it turns out it's only expensive if your operations are expensive. And like if you only have like 30 operations in your virtual machine, then the overhead is going to be 30x, right? If you have some operations which are like a lot more expensive than the others, the overhead would be like insane. And this is what we actually have with these hashes. So we need to solve the problem with hashes somehow. And with the way we do it, so yeah, we have like the problem is we have different operations which are like very, very varying in the cost. And the way we solve it is with recursive aggregation. So we have the basic circuit for the basic operations in the virtual machine, but all the heavy operations are going to be outsourced to different circuits which are way more efficient, which are optimized for this type of operation. And then we can combine them all recursively. And we use some nice techniques with passing we accumulate the queues of operations which we want to prove. And then we multiplex them through some hashes. Like it's actually very easy, but I just don't have time to explain it in detail. And we pass them to different circuits. And then we prove them in different circuits. And we enforce that actually every single operation is proven. That there is not a single hash, not a single storage access or signature check which has not been proven. So it has to all converge together, and we get the final proof which includes all of them. And the problem was with this approach that we didn't have the precompilers on Ethereum for curves which would be recursion friendly, but it was solved, and yeah, we proposed this the AP, it was never adopted. But we implemented the first recursive snark with Plonk. So we took the Plonk was invented by guys from Adstack, but we ran the first version on Ethereum, which actually worked last summer. And since then, it was possible to do all the rest. So we presented it first at the Reddit scaling challenge, and we brought it to production at zkSync 1 this January. And the rest was just engineering effort to build the virtual machine and to build the circuits that get connected together. Yeah, so it was not Turing complete, but now we combined. So the trick here is that like most of the TinyRAM approach is actually quite expensive. It has a very high overhead. The overhead is actually 1000x. So if you wrote a circuit for your smart contract natively, would be 1,000 times cheaper to compute than the circuit executed through this generic TinyRAM approach. But it doesn't matter, because the logic of the smart contract has like only very, very small fraction of the costs of overall contract execution. 99.9% of the costs go for these heavy operations like storage access, where we need to prove Merkle tree inclusions. We like Merkle accumulators is like the only working approach we have now. Maybe in the future there will be better cryptographic accumulators and it will be even more snark friendly, but for now it's that. Storage access, signatures, and access to memory, which is also separate, like it's separate circuit and pretty optimized. So we mixed that in. So I explained that. So yeah, in zkSync 2 we have this TinyRAM, optimized special circuits, and combine them recursively. And we actually optimized a lot of heavy operations, such as Keccak hash, which naively would cost you, like in Groth 16, the previous proof system which was very efficient up till Plonk, it would cost you something like 300,000 gates. Whatever that means, like it just translates linearly to the computing complexity. We managed to bring it down to 25,000 with very interesting tricks in Plonk, such as lookup tables and custom gates. And we did it for a couple of other operations, so it's very interesting. And yeah, what we do is we have a compiler based on LVM where we take the inputs in different languages. So we have Solidity, which produces Huel. We have zkSync, which just goes natively to LLVM. We will add Viper support later, which will also probably compile to LLVM, not to Yule, because Viper is not stake-based, which Yule expects. And then from LLVM intermediate representation, we compile it to zkEVM bytecode. And we ran a simulation on layer 1. So we took the execution trace of layer 1 transactions from like different DeFi use cases, some swaps, maker CDP, execution balancer, Aave compound transactions. And we ran a simulation to see what the costs are going to be. And we came to the pure prover cost of something like, as you can see here, hopefully, 0.01 USD, like 2 cents for transaction, 1 cent for transaction. So it's going to be the fixed baseline, which you always have to pay. Everything on top of that is going to data availability. So you will have to, like if you use zkRollup account, you will have to publish data on Ethereum to preserve the full security of layer 1. And by the way, zkRollup is the only scaling solution which offers like exact same security as layer 1, assuming bug-free implementation, of course. But like if you don't have bugs in your implementation, in your circuits, then it's exactly the same. Like you unlike sidechains, optimistic rollups, Plasma, anything else, it's exactly the same. Like no one can take your money from you. Eventually, you will always be able to get it back. But it has a cost. You have to publish data on chain. If you don't want to publish data off chain, if you just want to stick to this very low fee for like 1 to 5 cents, you can choose a different account type called zkPorter. And here's what it is. Why it matters is we all hope that rollups will bring the cost down. This will certainly going to be the case in the beginning. But they will very quickly be eaten up by very aggressive traders who will come and say, oh, we can do more trading now and do more stuff. And they're just willing to pay a lot. Like we saw it from the MEV world that they don't care. Like as long as you can make like 5% marginal profit, you're going to pay the rest to the fees. And this is going to affect all the other users. So we need a way to scale super linearly, not just like take the existing Ethereum throughput and multiply it by 100x. And we are going to have more use cases. Like we are going to have NFTs and all the users coming from different solutions to Ethereum because you can have it natively. So like more users, more use cases, and more frequency of transactions will lead the costs, the gas costs on Ethereum to go up a lot. And this is actually what happened. The number of users grew around like 1000x over the past year, but the gas fees rose a lot more. Now they are a bit down because of all the magic with MEV simplification and so on. But like, it's a one-time effort. Like we get 10x more users, the same thing is going to happen. So the solution to this is long-term is sharding. Like the only proper solution in Ethereum, the Ethereum sharding will bring a linear boost of scalability, but in the future we might have something like even more advanced with erasure codes and so on, but it will take years, like 3-5 years at least. For now, what we can do is we can separate our state into two different subtrees, and we just say like you as the user can choose which type of account you have. Is this account residing in the zkRollup subtree, or is it residing in the zkPorter subtree? And they are all the same for all practical purposes. They have these like normal addresses. They can address each other. They don't have to know what the other account is. You can use a transaction which spans across multiple types of accounts. But for zkPorter accounts, we don't publish the state updates, which we do for the zkRollup accounts. That's the only difference. So the practical difference for the users is just the cost is different. In zkRollup you pay more, in zkPorter you pay less. But the beauty is you can have users who are coming from like Binance Chain and all the other side chains back to Ethereum, but they don't care about security because otherwise they would not be there. Like they just want a cheap transaction cost. So they go create zkPorter accounts. They can use all the zkPorter stuff, like send money to each other for like 1 cent per transaction. They don't care. But they can still interact with all the services on the zkRollup side, and it's going to cost them less because we're going to amortize the final state updates to like Uniswap pairs to some data snaps in Uniswap across thousands of users who use it on the zk porter side. So even though they interact with like normal zk, like with the canonical Uniswap, where all the whales have their money with the huge liquidity pools, they're going to pay a lot less. Not 1 cent, maybe 10 cents, but it's going to be like pretty fixed. So that's what zkRollup is about. I can explain how it works, but I think I already did. So yeah, we just publish state updates on the left side. We don't do it on the right side, but otherwise the accounts are absolutely the same. And the data availability of zk porter accounts is going to be secured by a consensus of what we call zkSync guardians. Like these are token holders that are responsible for securing the data. And all they can do, like they cannot, all the transactions are cryptographically secured, so nothing can go wrong. They cannot steal, they cannot forge state, corrupt the state, but they could, if they collude with like 2/3 or like a super majority of the stake, they could freeze the state. So it's like it has the similar property to sidechains, but it's actually strictly better than a sidechain, and there is no incentive, like no way to directly exploit it. Because if they collude and freeze the state, their token is going to depreciate, and they could try to blackmail the users, but it's really hard to coordinate with those users. So it's a lot more hurdles for them than for sidechain operators who can just like grab all the funds there and exit. And they will, like, if the stake of the validators is greater than the total amount of value in the zk porter part, there is no way for them to make profit. They can only do it like as suicidal, being evil, but they cannot profit. So like there is no crypto economic incentive for them. But still, it's very important to decentralize the stake properly, and we're putting a lot of thought into this, how to do this. And the users are free to choose. Like you can for example have most of your funds in a cold wallet on the zkRollup side, and have like some small funds to make daily transactions on the zk porter to like spare the costs. Or maybe traders can go to zk porter, trade a lot, as opposed to like centralized exchanges, and then move all the proceeds back to zkRollup where it's safe at rest. So yeah, with zkRollup we have a cap on throughput of around 2,000, 3,000 TPS, depending on like how Ethereum, depending on the transaction type. So it's actually a lot cheaper than optimistic rollups because we can skip a lot of intermediate steps. Like we only need to publish the final state for each account on the zkRollup side. So like it's, in some cases it's going to be a lot cheaper, like 10x, 100x. In some cases it's going to be the same price. But yeah, all the rollups are going to share the Ethereum block limit for call data, so they all compete for the same data. On the zk porter side, on the other hand, we don't have that limitation. We can have like 10,000, 20,000, 50,000 TPS. The bottleneck is going to be the consensus of the validators, which is to be determined like what the upper threshold is going to be, but like a lot higher than Ethereum. And fixed cost versus a fraction of L1 costs on the zkRollup side. Yeah, optimistic rollups unfortunately cannot offer this extension. Also, sidechains cannot do this. Like they cannot have something which is like more secure than what they have, or less secure and cheaper. They have to stick to their paradigm. So like, if you go to like Polygon, it's cheap for you to transact there with higher risk, but then you have to actually exit your funds to Ethereum, move them to some other rollup, and then use there. Whereas in zkSync, it's going to be all seamless. Yeah, thank you. We have time for questions? No, I'm not sure, but yeah, probably yes.
We have 5 minutes.
5 minutes? Okay, we have time for questions.
Does anyone want to ask a question?
Hello, thank you for the nice presentation. So years ago, you talked about having ERC20 tokens on zkSync. So are you now going to put them into this paradigm and actually run an ERC20 contract? Or are you still having some custom solution for moving ERC20 tokens?
We will support ERC20, so you will be able to deploy contracts that support different logic and you can program them.
Thank you.
Hello. So, thank you. I'll use this. Just take it off to ask questions. So thank you for the presentation. It was very interesting. So my question is, what do you think of using the MIMS of hash function for the minimal multiplication complexity function instead of SHA-256, which basically decreases the number of field multiplication, of course, will decrease the constraints in the hash functions, for example, in zkRollup or other zkSync or something.
Sure. So when you compile your Solidity contract, you will be able to define, to say, like, all the hash functions, all the Keccak hash functions I use in this contract, do I really need to have them as Keccak, like real Keccak? Or is it like, do I use them because it's a cryptographically secure hash function? And if you, like, you will have like some manifest file for the compilation where you will be able to say, like, it's just a cryptographic hash function. So please replace all of them with the invocation of an algebraic hash function. What we're gonna use is Poseidon probably, or like there's gonna be some new hash function presented, I think in fall. But for now it's Poseidon. So we have two different functions used in our circuits. One is Poseidon, one is rescue. But rescue we use, like, rescue is proof system specific. So like if you change the proof system, like the results will change. So we only use it for internal bindings, for like this queues and stacks and so on. And for everything which users depend on to have the predictable outputs, we use Poseidon. But it's also very cheap. If you need to use Keccak hashes as a Keccak, because you take some external inputs from users, and you expect the users to produce some Keccak functions, you will be able to go on and mark them. Or either you mark your entire contract as like, please reuse the Keccak from Ethereum, or you mark the specific places where you use the real Keccak. But it's actually going to be very cheap. Even if you use Keccak overall everywhere, it won't add much to your contract. Unless you do like lots of those Keccak invocations, you can just do that and not bother, and it's still going to be like very cheap.
Okay, so it's no difference, basically.
Yeah.
Okay, thank you.
Hi, yeah, so you mentioned that EC Recover isn't supported yet, but that it's on the roadmap. Do you have an idea of like when that will be and how easy or hard it's going to be for you guys to add that?
We need to add, like, we have a concept of internal precompiles, like built-in functions which are going to be passed externally. Like we currently have it for system operations, such as like checking, verifying the Ethereum signatures, but we haven't provided the interface yet to access them programmatically from the code. Once we add that, we can add any number of those functions like Keccak and recursive code, recursive proof verification, so that you can verify Plonk proofs from your contract, which will allow you to build something like Zcash on zkSync with like super cheap transactions. So like your shielded transaction are going to cost the same as, like almost the same, like maybe slightly more than normal transactions, because you don't have to publish those proofs on Ethereum, even for zkRollup. So it will. I can't give you an estimate, but it's not complicated. It's just a matter of engineering. It's not something fundamental.
Awesome. Thanks.
Hi. Thanks. Great talk. What are some migration option paths between layers 1 and 2, and does it even make sense to support layer 1?
I think yes, because all the rollups are new technologies with, like the optimistic rollups have never been tested before. zk rollups have been live only for application-specific use cases and not with generic programmability. It will take time for people to gain confidence in those technologies. You need like half a year, maybe longer, for like a lot of money, a lot of people willing to experiment, to use the systems before the general audience and like people with a lot of money, with the whales, get confident. And meanwhile, you want to support the layer 1, and our approach is to make it compatible. So you can build the same code can be reused between layer 1 and layer 2, you can have tests that cover both parts, and you can be sure that they will always compile. And then you can migrate gradually. You can deploy both versions on like layer 1 and layer 2, and then gradually move some of your users, or your users will decide to move part of their value from layer 1 to layer 2, and like gradually this ratio will change, favoring the layer 2.
Awesome. Thank you.
Thanks again for presentation. It's very clear, but I have maybe a stupid question about zk Porter accounts. Imagine like DeFi situation, Uniswap pair, and I as a LP provide some liquidity, and like only zk Porter account trades on this. And as a liquidity provider, I depends on validators, because while like all this trading, no proofs has been published. And in this situation, it's equal to optimistic rollup. Is it, or maybe I missed something?
So again, your LPs have put some...
I provide some liquidity to Uniswap pair and forget about it. After that, like people that use zk Porter accounts trading heavily, but during this transaction, as I understood, they are not publish proofs on chain.
Yeah.
Only validators.
But you as an LP, you submitted your liquidity from a zkRollup account.
Yeah.
Then you're safe.
Yes.
So like if something happens to zk Porter and the state is frozen, all the users with zk Porter accounts will get frozen. They will not be able to access the funds. But all the users with zkRollup and all the interactions they had with the zkRollup contracts, and most contracts are going to reside on zkRollup side. I can't imagine someone deploying contracts on zk. It probably won't be allowed. You always have to deploy contracts on zkRollup side. You're fine. Like in Uniswap, you have your like balance mapping, which says like Uniswap owns you so many tokens. Like you have this position there, right? So like as long as your account is on the zkRollup side, you can always access this mapping and it will work. If someone from a zk Porter account will try to access it, it won't work for them because the data is not available. But you will be fine.
Thank you very much. Unfortunately, we have to
Sure. Thank you, guys.
leave the stage.